Alrighty, hello. Um, my name's Ethan Rudy. I guess I am responsible for the making of this video. I I started to have an interest in like CPU architecture and everything through my schooling here at Arizona State. It started with CSE 230, which was an introduction to kind of like the idea of assembly at all and CPU architecture through a language called MIPS. But it seems that my mouse thing is a little. I have a little drawing tablet pen that looks like it is not mapped correctly. This needs to be landscape flipped and the full monitor. Okay, now, yes, there we go. Now I get to live out my dreams of being Sal Khan. There we go. We love to see it. Okay, so yeah, I started having an interest through CSE 230, um, through MIPS. Do I remember what MIPS stands for? No, but I do remember from lectures that this is used. It's the 32-bit system, and it's usually used in like embedded systems. Now, do I know the exact definition of an embedded system? No, I do not, but in my eyes, it's like a microwave, like a car, you know, an alarm clock. Now, obviously, like alarm clocks and stuff, they don't need a 32-bit assembly language, and they probably don't. Um, but something that is, you know, I guess the phrase keep it simple, stupid, or keep it stupid simple. Um, so like nowadays in like modern computers, we've migrated. I don't want to say recently because it's been probably for the most of my life. I'm only 20. Oh my god, I'm old. So we don't really use MIPS in our daily life when we use like our human human computer. Like your laptop will not have MIPS on it. My desktop does not have MIPS on it. This computer that I'm running this on does not have MIPS on it. But it was a good start. It's a simpler idea, and it's easy enough that you can just like compile it on the web. And I went from 230 into something called 365, which is information assurance, but that got us into x86 64, which is 64 bits in our case, and this is something that like modern computers use. We specifically use it. We specifically used it in creating web servers, and since it's information security, it's kind of like the intro to cybersecurity class, which is coincidentally my major. I'm a computer science major with a concentration in cybersecurity, so I love this kind of stuff. It's cool to me. So we learned how to decompile things, use IDA. I've been learning Ghidra lately for the hacking club here. I've been enjoying it a lot. So I like to think I know a little bit more about x86 than, MIPS, just because I've used this for, more than just a semester. So I kind of started when designing my architecture. I tried pulling from things that I liked about MIPS and things that I liked about x86, and kind of created a horrible brainchild out of the two. And you'll see why I describe it as horrible. I'm not exactly proud of it. But through my own time, which I'll just say my own, um, I played this game called Turing Complete. Now, if you are unfamiliar with what this phrase means, don't worry. It's okay. I'm gonna make it sound not complicated, but of course my professors like to make it complicated because in reality, I guess you could make it complicated, but we're gonna keep it So, you don't have to have an idea of like full on computer education. Because I was able to do it with not even a bachelor's. I'm still working through that one. But Turing, Turing, relating to Alfred Turing. I'm not gonna call him the father of computer science, because don't get me wrong, he's like up there, but I feel like that does disrespect to the mother of computer science. Um, so just know this guy was kind of like, he wasn't like computer science or I don't know. He was, I guess you could say, more of computing in general. That was kind of his thing. But what? So little history fact. But Turing complete means, at least outside of like pumping lemma or like any like actual theory. If you like just look up what does Turing complete mean, it means like calculate anything. So modern computers, as you know, are Turing complete. They can calculate anything, of course, given an amount of time. I don't care if it's till the heat death of the universe. You know, time is infinite, therefore, given enough time, you can find something. So the game is called Turing Complete, is what I'm trying to get at. And that allows you, I have it actually pulled up over here, Turing Complete. You can get it on Steam for like $10. It's a game all about making your own CPU architecture. So I played through it probably about to pretty much CPU Architecture 2. It's like a campaign with a bunch of levels. And that's when I kind of stopped the first time and I came back to it. But I mean, everything starts off with a simple wire and then a NAND gate with a truth table down here. So NAND gate means not and. So if you have input 1 and input 2, the output will only be on if not and. So as you can see, it's on if not and. We're looking for both of these to be together, right? So it's going to be on, off. Congratulations. Lore-wise, why this guy looks like this, you were abducted by aliens and they're making you build a computer. A NOT gate is just inverted outputs. So hooray. Oh, and everything in the game is built out of NAND gates. So that's an interesting challenge. Now, of course, you build, this NOT gate is technically made out of NAND gates, but they simplify it down for you. So an AND gate, of course, is a not NAND gate because, two NOTs make a positive. So you're negating a negation. So it's you get through basic logic. So let's say you have a XOR gate, and a XOR gate is an exclusive OR gate. Because if we go look at, where is an OR gate? Probably down here. OR gate, yes. So OR gates will be on if either or both of the inputs are on. And then a XOR gate, which is like really, really important, is on if only either or, not both. So none are on, left is on, right is on, but if both are on, it's off. So you go through all that, you get into like doing arithmetic, like byte adders and everything, which I won't really be going into because I am hoping if you are watching this, you have an interest in the subject. And normally if you have an interest in a subject, you normally know a little bit about it. But up here in the CPU architecture, you can see the first, like, I guess, CPU that you make. So it just kind of sits here. So there's a lot of stuff going on here, but just to give you an idea of how the level works is how the game works is you create a CPU, right? And this is a single instruction, I guess. Single instruction. right? So you make a single instruction CPU, which is pretty much you can load something into register 1, then load something into register 2, and then add like this. That's all it is. There's no move, there's no copy, there's no save, there's no stack, there's none of that. There's no functions. All right, so it's there's I don't even think we have a jump. So very simplistic, kind of mid. And this was called I think this was called the Overture architecture. This is an in-game name. It's called Overture, I'm pretty sure. And then you get into, I would say, like more of a MIPS style architecture where you can say like, you know, move the input into reg 1 and then move input to reg 2. And you can say add and store it in register 3, reg 1, reg 2, right? And this was something called the leg architecture. And you could, this was to like teach you, and this is when you started doing other tidbits, and I just realized that I'm kind of leaving some stuff out. Reg 1. Oh, that's a line. I don't want a line. I want this. Here we go. So I'm just going to call this multi-part instruction. And we'll call that leg. Of course, they're all capitalized because they all mean something. Do I remember what they mean? Not at all. So I'm not gonna try to make something up on the spot and lie to you. So, and you could finish the game on this multi-part instruction CPU, but I was not satisfied with this. I wanted a multi-part variable length instruction CPU. And what that means in our case, if we were to look at some opcodes and registers, or I guess, yeah, let's just go down to the bottom here for some written examples. So, what does variable length mean? At least in our case. Like, in reality, there's normally like padding and everything that goes into this, like immediate instructions. They have different padding to hold larger values, a bunch of more complicated things that people got paid a lot of money to do that I was not, because I did this in like a weekend in my free time. So if we look at, I believe I called this an R-type instruction, which means just like a regular type, like add a source, a source, target, and a destination, right? So there's 4 parts. And I should have mentioned that this architecture, mine, which I will go back over here, and we'll call this TRZ. This was 8-bit. And then we had TRZ2, because this one failed. And this is 8-bit. So everything here is 8-bit. Or aka 1 byte. And I believe this was 8-bit as well. But it's been literally months since I did that one. So don't quote me on that. So if we're an 8-bit computer, that means we can store 8 bits worth of numbers. So that means we can have 8 bits, which is 1, 2, 3, 4, 5, 6, 7, 8. And I'm not going to give you a rundown on the binary, of course, but 1, 2, 4, 8, 16, 32, 64, 128, meaning we can store positive values 0 to 255, because 256 is the 9th bit. And then if we were to sign these numbers, meaning add a sign to them, positive or minus, we could split it down kind of the middle, because 0 does exist. Negative 128, I believe, all the way up to 127, because 0 is on the positive side. Meaning we can store values like this. So if each one of these is an 8-bit value, that means we have 32-bit instructions. And that is what TRZ used, and that is what LEG uses, 32-bit instructions. And that's like the 32-bit instruction width, I should say. So each of these, you know, an add has an opcode assigned to it, an operation code. It's how the computer knows what to do. The opcode of add is different than the opcode of subtract. Same with multiply, divide, move, all this stuff. And so this is 8 digits, 8 digits, 8 digits, 8 digits. 8 times 4, of course, is 32. Now, I have more than just R-type. Now, let's say we have a J-type, right? And a J-type in my case means like jump, right? So I get this is the closest thing I could think for like an unconditional jump, right, is like a go-to statement. And like, I don't know, I guess basic. You know, it's been a long time since go-tos, I guess, have kind of been acceptable, you know? Now that we have function calls and stuff, we don't really need go-tos. You know, you can get around it in a safer way. But let's say we were jumping to a label, right? Where jump, of course, is an opcode. So it's 8 bits plus 8 bits. Means this is a 16-bit instruction. Instruction width. Now, of course, when we are programming something, we have a stack pointer and everything, which, you know, it's kind of tells the computer where it is reading, like what code from what memory. So if you're jumping, in this case, everything is split up into 8-bit chunks. So if you're jumping from an R-type to an R-type, it's a 4-byte jump, right? It's two words. A word is 2 bytes. All right, so it's a double word. So it's a D word. I'm just gonna call it a 32-bit jump. So it's a 32-bit jump. But if you did a 32-bit jump after a J-type, let's say you had jump label, and then add R1, R2, R3. If you did a jump, you would be skipping add R1 and just immediately jump into R2, and then you would be grabbing like, then you'd be reading like an instruction like it's like this. And then so you're off kilter, right? Which means, and which I did before in regular TRZ, I guess 0 or 1. The first one that I ended up not finishing, you would have to pad it with like 0 and 0. Or like null. I ended up just calling it, I ended up just having like 0 be a reserved like thing. It was kind of stupid. I hated it. It needed a lot of like spaghetti wiring. So I decided, you know, real computers have variable width instructions. Why can't I? So that's kind of the differential between TRZ and TRZ2, and that's the part that I'm kind of proud of. You know, like designing your CPU. You know, once you get the theory and once you read enough about pipelining and stuff, you're fine. So if we were to kind of talk about the instruction format, I have an R type, aka a regular type, a jump type, an M type, an S type, and of course, with anything in life, there are exceptions to these types. And that is handled through something called pseudo instructions. Now, you've definitely heard that word before if you know anything about MIPS or anything like that. What that means in MIPS is not what this means. I kind of made my own definition. A pseudo instruction is an instruction that matches the paradigm of a type, but with a different instruction width and or byte order. The instruction decoder manages the conversions and the byte alignment. So an example of a pseudo instruction is a bitwise not. So a bitwise not would be like not, so you'd like not A and put it in B, right? So it'd be not A, B. or in actual programming, it'd be like that, because everything gets stored here. Now, this is something called a bitwise operation. And that means if we have not 1, so not 1, binary 1 is 1, 2, 3, 4, 5, 6, 7, 8, right? If we were to not, aka inverse, it'd be 1, 1, 1, 1, 1, 1, 1, 0, right? And that becomes 100, 254. 254. There we go. So this matches the bitwise paradigm of ANDing something, AND A, B, and putting it in C. But as you can see, this is 8 bits shorter. So not is something we are calling a pseudo instruction, because it follows the paradigm of, like, let's say an arithmetic function, but the byte order can be a little bit different. And that's like, you know, popping and pushing from the stack, because, you know, I call them source, target, and destination registers, but they don't always serve the purpose of being the source register. Like if I pop into R1, yes, this is called a source register, but it's acting like the destination register. So this would be an example of a differing width, and this would be an example of a differing byte order. So one is the instruction's legit just a different size, and the other one's we need to send this data to some, you know, to a different register. So the 4-byte are, you know, arg1, arg2, and a destination, and that is arithmetic, because, you know, you can't really do a lot else on a CPU without syscalls. That's not arithmetic. So you can see we have a pseudo instruction for a 3-byte not, which is an opcode arg1 and a destination. So arg2 acts like the destination, but it still gets sent via the destination line. And then you got a 3-byte move/copy, which is just adding 0. That's all it is. But instead of saying add R1, 0, R2, you can save a byte and make it a pseudo instruction. And then pseudo instructions for 2-byte move from low and move from high, MF low, MF high. We will talk about that. But then you have a couple of jump types. Jump type, again, 4-byte. I decided to make all of the jump types. So jump if equal to, jump if not equal to, jump if less than, or equal to. Sorry, I lost track. JLTE, JGT, JGTE, and then, of course, just J. Now, these all have a format of opcode, R1, R2, and then where. You know, where are we jumping? This one is just opcode where. Because we don't care about an operation or anything. I don't know why this thing doesn't want to erase today. Alrighty, wonderful. So that's this 2-byte jump unconditional. I call it an unconditional jump just to differentiate it. And then we have M types, which are memory types, which are normally 3 bytes. So that's like save and load from RAM. And then I have S type, which is stack type, which is you know, pushing, popping. I even have call as a stack type, because, you know, it's pushing the stack pointer and everything. And then 1-byte return, you know, you just say the word return, and it returns. So you can kind of see opcode is the operation, arg1 is argument 1, arg2 is argument 2, dest is destination, SP in this case means stack pointer. It's like the program index. I'll point it out, and IW is instruction width. So you can see all my opcodes. If I was to do this next time, I would not have these by like paradigm. So I have add immediate, subtract, multiply, and divide. You can see what they are, the action they perform, their opcode, their decimal opcode, their type. Are they a pseudo instruction? Their byte width, and then their byte alignment. It's like if we get into something that's not like a regular pseudo one, here we go. MF low, right? So move from low, MF low, R1, right? Register 1 actually needs to point towards the destination register because everything has its own line, right? It has its own data line. Register 1 has its own data wire. Register 2 has its own data wire. And then destination has its own data wire. So it's kind of like just subverting the expectation of where things are going. And then right before we actually get into what it looks like, I want to go over my registers. So I have, I believe, 17 registers, kind of. It's more like 15. Input and output are just data from the game itself. It's, how you actually play the game, and now it's not just a sandbox. So 0 has an address of 0, just a constant 0 value, just whenever you need it. It's read-only. You can't even overwrite it. It's just the write pin isn't even connected to a wire. It's physically impossible. And I have 8 general use registers for everyday use. And then I have read-only low and high registers. And we'll definitely get into that next. So if we were to actually go look at the last level of the game, this is my CPU in its entirety, because I put a lot of stuff in custom components. But if we were to look at our program, right, see how this width is 4. It's gonna read like 4, but I have a counter to manage this. So if I actually go to run this, see how we actually go to 3 instead of by 4, and now it's like 3, and then it'll be 6. So we're jumping by 3, but now we're jumping by 4. So it's quite nice. But you can see I have an opcode, argument 1, argument 2, and destination line, and they go into an instruction decoder, and that gets sent all the way over. But before we jump in anything crazy, I just want to kind of point out the kind of like the parts. So you have the instruction decoder. This is what handles the byte alignment and everything. This is kind of like the overarching, like, actually cool part about it. The rest of it is a lot like the game. So we have arg1, arg2, and a destination. So anytime you see these teal lines on this level, they're argument 1, just like these purple lines. Teal and purple is argument 1. Orange and this kind of weird indigo blue is argument 2. And then this minty color is our destination. So you see we have a register, right? And our register has a load pin, a save pin, a value to save, and a couple output pins. I don't think I actually end up using the always output pin. You're right, I do not. So as you can see, these teal lines get ORed together and put into the load value, right? And what these do is they just activate the value, right? They just unlock a register, right? I guess I don't want to make a Minecraft Redstone analogy because, what do you think Minecraft Redstone is modeled after? But that's exactly what this is. It's just like a flip-flop. And then because the game has short circuits in it, I had to have everything on a switch, which is kind of annoying. But the actual save pin is always referenced by the destination. And this gray line is the result that comes from either like the input down here or out of the ALU, which is very, very nice. So I can juggle these and throw these on the lines and either send them to the ALU. I can send them to output over here, or I can, of course, send them to the stacks, plural, kind of weird, or RAM. We have the ALU over here we have the read-only registers down here, low and high and 0. Yeah, we have RAM and then like the program stack. Because one thing I always hated in like MIPS and everything was accidentally pushing and popping to the stack and like getting lost when like passing things into functions and stuff. So I decided, screw it. Let's just have a stack for like the actual user and then a stack for just program flow. And it's come out pretty nicely, not gonna lie. If you're seeing like these other lines come off the instruction decoder, that is the high-low enable pin or the immediate pin. I'll go over the high-low pin first. The high-low pin is what enables high and low to be saved to. Because sometimes you don't want to overwrite it. Like you don't overwrite high and low on like an add operation. You only use high and low on multiply, divide, because divide also gets you mod. I think that's the only time I use high and low in here. But that's just like the enable of, store the value here instead of anywhere else. And then the immediate value is, you can imagine, it would be pretty complicated. Saying, okay, I want to add 5 and 4, right? And let's say this is in memory and 4 is not in memory. Anything that's not in memory that we want to do an operation on with like immediately, of course, is called an immediate value. Like you can just say add I, register 1 and 4, and it'll just give you it. So add I, instead of acting like these are both registers, it says, hey, don't unlock this register at this value. Instead, use this value like the output of the register. Just so you don't have to say, load 5, load 4, add both these together. It's just, 5 is already here, let's just add 4 to it. It's completely just for ease of mind and use. Like you could, I think TRZ even had a sub I, a mul I, and a div I. And I even have jumps that are immediate. Pretty cool. Do I have them all written down? No. Are they available to me? Yes. Will I ever use them? No. But I think it's cool that it's an option. So the immediate value, as you can see, just comes along here, and it takes the value in register 2 and just muxes it right onto the line. Mux meaning multiplexer, meaning that whichever one I select, 1 or 2, it will select from input 1 or input 2. So it's, instead of like an on-off switch, like yes, allow data or not allow data, it's like allow data A or allow data B, depending on if the line is enabled. So it's another way of getting rid of short circuits. Like I do the same thing coming from input, just so I'm not accidentally short-circuiting input with something coming out of ALU, because you can see ALU just kind of always output 0, because nothing's happening on it right now. Given that I haven't like put a switch on everything, and that would be kind of tedious, I just decided, okay, let's just mux things. Save me some processing power, because sometimes this can get a little laggy. Yeah, I mean, a lot of this stuff isn't that crazy. Like the stack is just RAM with like incrementers and stuff. It's not like anything super crazy. It's just like when you push something, you save where you are, then you increment a counter. And when you save something, you increment. It's a very simple data structure. You're looking at RAM right here. Has a load, save, an address, and a save value. So it's super easy. Argument 2 is the address, and argument 1 is what you want to save. So it would be in the form of, I want to save the number 5 into address 4, right? So you would say save, let's say this is an R1, and you could even have a save I, which I don't, because I feel like I'm going to break something. Let's say this is an R3, and then it's in RAM. And it's pretty nice when, you have a program that you need an array with, but you don't have pointers. Very fun. No pointers. Makes my life incredibly difficult. I miss programming languages. They're so nice. Before I go into instruction decoder, I kind of want to go into what a program actually looks like. So you can see all of my assembly codes over here, right? And it's like a full-on text editor. It's really nice. This is a very common programming problem. It's like, how much water can you fill in this world without spilling? It's like you can put water. I guess I should probably just draw something, right? So let's grab a rectangle. Let's grab a rectangle. Let's grab a rectangle. And only 2 more rectangles, I promise. And we'll put, let's see, another rectangle. Why not? It's like this, right? Now we know if we were to just pour like water down into this, we could only fill it up to here, because if we put water in this block, it would spill out over the edge. So if you look at this, you can see we can fill water in here, we can fill water in all of this, we can fill water here, and we can fill water here. If we were to fill water up here, it would spill out the edges. That's not what we want. So it's a program to find how much water you can put in it. But like it just looks like straight assembly with like labels and everything. There's no unnecessary padding, like loading register 1 from register 8. Sorry, register 2 from the address in register 8. So like it's really well done. But the main thing I want to touch on is the instruction decoder, because the instruction decoder is what tells the counter, the better counter. Like it's straight up just a counter with how much you want to jump by. It's that simple. So the instruction decoder, when you go in there, it's actually 2 things. It is an instruction byte width finder and an instruction aligner. And of course, these work in tandem. So if we look at the byte width first, you can see it's kind of a lot. You can actually see the way I'm mapping this. This is how I built that table over on that document earlier. You have the opcodes, 0, in this case up to 63. Could you have more? Yes, you totally could. So you have like arithmetic, bitwise, memory, stack, and then some like weird stuff that I ended up adding later because I was like, oh my gosh, how did I forget that? Like TRZ, the original architecture, I was texting a buddy about it. I was just like, am I missing something? And he's like, dude, you're missing an unconditional jump. And then you have the jumps. But like grays are regular types, white is pseudo instructions, and then the different colors of blue, green, yellow over here correspond to byte width. So it's just like a manual decoder. It's really sucky. If you actually wanted to look at the opcode decoder, it's even worse. Like, it's a 5-bit decoder. Like, there's no easy way of getting around that. It's just gonna suck. It's just a lot. And of course, there's an enable pin. So everything has to be ANDed. So that's part of why the gate score is like 21,000 gates or something. It's way high up there. But I mean, this one, it's easy to wrap your mind around of if I planned this out and I built it and then it worked, right? Did it work the first time? God, no. But if we look at the actual instruction aligner, this is where things get a little weirder. So this is what I was talking about, that byte alignment stuff. So if we looked at move, right? This is the instruction for move. So add and 0, and then 1, 1, 0 is 2, and then 2 is 3. So we're automatically moving the opcode for add in it because we want to add something in 0 and put it in there. But we only want to take up 3 bytes instead of 4. So you see I'm shifting stuff down to the destination and adding in 0. And all these multicolored lines are just like hard-coded things for add, 0, low, and high. And their addresses, so like pop, load, jump, return. I made return a pseudo instruction, even though things aren't aligned differently. So technically I could just pipe this through, but I wanted to have it here. And obviously MF low and MF high, the only difference here is where they're going. So like their alignment is exactly the same. Then you have not, not in the ALU only takes one register, so I just pipe 0 into it. And this gets sent out from, destination, opcode, arg1, 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 arg2, and then destination. And that becomes the new opcode, arg1, arg2, destination. And then the high, low enable based on the instruction, and then the immediate flag. Based off, of course, all the opcodes. So a lot of this is just like piping data past and past and past. Well, you can kind of think of them like functions that are being run, but like you have like a function that you need. It's like a function inside a function inside a function, but like the data that you need is so far out of context that you have to like tunnel it through a bunch of functions. Are there better ways to do it? Of course. Am I smart enough to do that? No. Obviously, the 4-bit decoders are just a 4-bit decoder. I already showed you stack. If we look at the ALU, of course, made out of 2 things. Could I made it one thing? Yes, I did. Was I smart about it? No, I was not. So we have a math cube, and then the infamous perfectly square cond cube. So arithmetic, and then conditionals. So we look at arithmetic. It's pretty simple. I mean, I already designed the divide chip, right? So I don't need to, make a whole divide circuit. I built it once and I can use it again. So we'll get into why high and low exist at this point. You'll see that high is, I think everything goes into low first. Yeah, low, everything gets sent to the low pin, no matter what. Whether it gets written to the low register is a completely different thing. But only a couple things use the high pin. If you see these like weird, like always on pins, it's just for the actual shape of the opcode, like the opcode math right here. Like if I was to get rid of this on one, that corner would disappear. It's purely for aesthetics. But you'll see that all these just use the purple one, but divide and multiply use the low pin. You're like, okay, Ethan, why do they use the low pin? Before we get into that, divide does have a divide by 0 flag on it. So if you do ever divide by 0, your computer isn't just going to crash. It's just going to make that 0 a 1. So if you accidentally divide by 0, nothing will happen and your number will not be modified. Was that the correct way to do it? No. Did I do it that way? Yes. Oh, and then of course, not does not have a second argument. Like we were talking about earlier, shows it's the pseudo instruction. Very, very fun. We will go ahead and cover the high-low register before I forget about it again. So let's think about arithmetic for a moment. If you have, let's just stick with 4-bit arithmetic right here. And you wanted to add 1, 1, 0, 0, right? And you wanted to add these. And let's assume that these are unsigned, right? So it's only positive. You'd have 1, 0, carry the 1 because this is binary, meaning you only have 2 digits to work with, by 1, 2. So you carry it 2, unlike our base 10 number system where you carry it 10. So instead of the 1's place, 10's place, 100's place, you have the 1's place, the 2's place, the 4's place, the 8's place, and so on. So these get added up. These become 0, and this gets carried. This becomes 1, right? So that's fine. of course, there is the problem with overflow. Do I have an overflow detector like MIPS does? No, I do not. Because imagine if you did 1, 1, 1, 1 plus 0, 0, 0, 1. This would end up all kind of like cascading and be like this. But of course, we can't store this. So instead of being 1, 2, 4, 8, instead of being 9, and instead of being, what is this, 15 plus 1, instead of being 16, this would actually just be 0. That's called an overflow. You're overflowing the amount of space you have. And of course, if you were to do it in the opposite direction, you would then underflow. Just in a limitation of our technology. We represent infinite series with finite space. I'm going to plug something right here. I'm going to plug big integer. It's an arbitrary sized integer class for C++ that I spent like a year on. I've literally been coding it since I was in high school. But it gets rid of over and underflows. You just have to have enough space on your computer to hold them. And that arithmetic works, right? That arithmetic works with one output register. Now, I want you to start thinking about multiplication. 1001 times, let's just do 1111, right? So we're to do multiplication be 1001, append a 0, and then 1001, 1001, 1001, and these are all filled with zeros and stuff. So you would have 1, 1, 1, 1 or something. I don't know. I completely came up with these numbers on the spot. Now notice how this is 4 bits and how this can be up to 4 bits. Meaning that when you multiply, you can have a result whose bit width is double what you had before. It's base 2, it's double. Now that's fine. That's like an intuitive high and low. So like the high register would hold the upper, the higher bits, and then the lower would hold the lower. Now, of course, this is, 4 bits, but mine is just 8 bits. So my multiplication can result in 16-bit values. So to get around that, and let's say I did need the upper 8 bits, or I needed to kind of finagle some values, that's how I would do it. Division is weird. Do I remember how to do bitwise long division? No. So I'm going to just do regular division, right? So let's say you had the number 15 divided by 7. Now we know that this is going to go in twice with a remainder of 1, right? Because 7 times 2 is 14, and then 15 minus 14 leaves 1. Because if we tried to put 3 7s into 15, we'd be at 21, and it would not be division anymore. Now, we all know via long division, in order to find the remainder, you pretty much have to find the quotient. And when you find the quotient, might as well keep track of the remainder. Can't really get one without basically finding the other. So guess what? Low holds the quotient. And now high holds the remainder. And this is the standard. This is not something I came up with. This is in MIPS. This is in x84. There is no mod function, right? There is only a divide function. And what you do with the result of the divide function determines what operation you cared about. That's the reason I don't have a div and I don't have a mod. Because, those circuits would be exactly the same. It should be, instead of this wire, it'd be this wire. And, that's just a waste of my time. And also, I don't have a mod circuit. You didn't build one in the game. It's not even made. So that's what high and low hold. Anything where there's like two results or a wider result goes there. So, there's a lot of like things that we did here. Like this one, I had to sort these like within. I had to sort these in RAM. So it's legit just an insertion sort. So like you can see it's starting to run over here. It's like 251 goes to the end and like 63 will come over here eventually. But it's like an n squared algorithm. It takes forever. So if you just run it, it does tens of thousands of ticks per second and then it finishes. I'm trying to think of things that I'm kind of proud of. Okay. This one is a good example. If we were to look at what's going on over here in this program, we would call a function called move, right? And move is just a bunch of numbers. Now, we're controlling this. This is the part that makes it the game. Our input and output is this game. The input is whatever the robot is seeing, and our output is an action that the robot will do. So we have an action to move, like rotate left or rotate right, and then move forward or back. Oh, more like just forward. So you can see we move our robot, right? And now we're seeing 92, which is the conveyor belt. And this is where we return. We go back up past our label, because the label isn't code, it's not executed, it's just a point in memory. The goal of this is to wait for a duplicate fruit, not an apple directly after an apple, but an apple like 8 fruits since the last apple. So we have to use RAM for this one. So we await, right? And we are just checking and seeing if register 1, what we are seeing, we're getting input, putting it in register 1, we're saying, hey, is whatever we're seeing in register 1, is that equal to 92? Because 92 is the conveyor belt value. And if they're not equal to it, we jump to fruit, which handles our fruit logic. But right now, we are just going to continue to await. You know, if we don't jump, we can just loop. Okay, wonderful. We are seeing a pair. So we get our pair. Look at this. We're not equal to. So our condition will say, hey, jump somewhere. And it goes into our better counter. And then, boom, we jump down here. And we clear out whatever is in register 8 by XORing R8 and R8. XORing a value against itself will always just zero it out. And then we loop across our RAM. We're just looking for something. We're looking for our first non-zero value in RAM because we need to store our value, right? And of course, we found a 0. And is it found? No. So it's going to keep going. So we had a pear. Now we have a golden apple. Now we have a tomato. And we have an orange, and now we have a kiwi, and this golden apple should be our next catch. So we click through. Yes, we're seeing a golden apple, which is at RAM address 1, because everything is addressed at 0 in computers. Hooray! So we are going to see that we have a fruit, and then we're going to iterate across the RAM. And then, well, register 1 and register 2 are equal to. And it jumps to the end. And the end is we just have to rotate and press this control panel. Hooray. So it's like very gamified assembly. Like there's a Tower of Aloy program, which was really, really not fun. We actually show it. It's like you have to move all of the tower pieces to the side. But we have to move from 0 to 1 without putting like a 1 on top of a 0 or without putting a 2 on top of a 3. So the lists have to be in descending size. So it's kind of like a really, I feel like it's a Cracker Barrel type game. If that makes sense. Like I feel like it's something you'd see on the table at Cracker Barrel to keep yourself like occupied, you know? You know, it's a very I feel like it's Conway's game of life. It's just like a thing that people know. Planet names. This one was really simple. So it's just going through and capitalizing the first letter of every word. So you're just detecting a space, and if it is, you know, it just reads you ASCII value. So you just you just do the ASCII math with an ASCII table. But I like seeing all the numbers flash by as things actually work. But it's very, very fun. So it's completely functional. Were there bugs? Yes. Did I solve most of what I found? Yes. There's like even a pseudo random number generator where I like dances. And I guess we'll get into Waterworld because it's like the hardest one. Now you might be wondering, Ethan. Oh, sorry, I should sit up. How are you saying register to? You know, like what is that? What does that actually spit out? Right? Like how do you know this is move an input R1 and then something I don't care about? This is actually technically reading the save opcode, but notice how it's just getting zeroed. So we're not reading anything we shouldn't be. But given everything is just numbers in disguise, if we go look at move, we see it actually has 0. And then the input register, it's read only. Where is it? There we go. Actually has an assembly code of 15, which matches. So yes, I had to hand draw out all the binary for all of the opcodes I want, which is why sometimes you say jump less than plus 64, because I can actually just say save plus 64 and make it an immediate value without having to like make a whole new instruction for it. So if you see like a plus 64 somewhere, I'm just making it an immediate value, which you can obviously see by argument 2 being an immediate value. But the way we go across and we run this, if I show you the RAM while this runs, this tells us the highest point of this. My input will be the height of the land when I go across it, right? So 4, 6, 1, 4, 6, 5, 1, 4, 1, 2, 6, 5, 6. And then so I have like the most I can fill to the right, right? If everything is 6, I can fill 2 and then 5 and then 2. So we do like a right pass, which I figure I should probably just draw out again, not going to lie. Because I showed you the problem, but then I didn't talk about the problem at all. Don't worry about the alignment. We're going to change the size of all of these. Make this like half the size. We'll do like this. We'll do like this. Do like this. Do like that, I guess, and then like this, right? So first off, we do a right pass, and I will do the right pass in green. All right. So on the right pass, I just realized this is kind of a shitty example. We'll do like that. So on the right pass, we're like, okay, we are hitting 6, so we can fill this water. We can fill this water. We can fill all this water. And, dude, this is such an awful example. I'm trying to... the first time I recorded this, I had such a better example. Okay. On the right pass, we see, okay, we can fill up to here, we can fill up to here. Okay, we can fill here. We can fill here. We can fill here. And we can fill here. All right, so that's the right pass. That's as we're going this way, right? Because we see we're 6. Okay, we can hold 6. Okay, we can hold 6. You know, let's say this is 4 actually. 4, 2, 2, 2, 2, 3, 1. Right? So we're like, okay, we can hold 2. Okay, we can still hold some because 3 is still less than 4, so we can still hold water. And okay, wow, we can hold 3 here. Wow, we have a lot of water. We can hold this all. So that's kind of like the right pass, right? And then we'll call the left path T. Well, it's kind of like weird, sucky brown color. It's like, okay, 1. So we hold this value. We can't fill anything here. 3, we can't hold anything here, but 3 is larger, so that's our new hold value. So now we know we can fill here, and we can fill here. We hit 4. We're like, okay, we can fill here. So this now gives us, if we go in and give these numbers some value other than the height, we'll have these values be how much we can store, right? So it's 0, 0, 0, 2, 2, 1, and 3. If you are then the left path is green, the right path can be 0, 0, 1, 1, 2, 2. All right? So now we kind of have like a weird idea of, you know, how much water we can flow in from both ways. And the lesser of these two values is how much we can store on that column, right? So we can store 0 water here, 0 water here, 0 water here, 1 water here, 1 water here, 0 water here, and 0 water here. So we can only hold 2 cubes of water in here. So I have a left to right pass and a right to left pass. So you can see the left to right path. And then you can actually see me going across and saying, since this is 4, it's going to be 6s all the way across, because that's the highest we can hold. And now I'll start reading right to left. So our lower value is 2, 4, and then it's 4 again. And I do all that comparison in the left to right. And then we have 6s all the way across here, because this one's a really bad example. And then the last little bit is just reading across the RAM and subtracting 6 from it, because they're never more than 6. But you can see I'm just treating the RAM like you would normally just like use an array for. You see we're up on 5s. And this is the actual water loop. And of course I wrote little helper functions for saving 2 mmH. Do I remember what mmH means? No. But it does exist. But you can see I pass all the test cases they give me, which is there's 128. Quite the amount. So like on this one, you can only hold 5. 1, 2, 3, 4, 5. But I'm very pleased with it. It is something I'm deviously proud of. I'm trying to think if there's anything I missed. Oh, I guess we could go back and talk about the conditions. Like the conditions are really easy. It's just a different type of ALU. That's pretty much it. It just tells it if it's true or not. And of course, if it's true, the better counter holds it anyway. But I just, I wanted to put it on my portfolio, but I wasn't really sure how I wanted to put it on my portfolio. And I, frankly, after writing the big integer documentation, which was like kind of grueling for me because I'm so tired of the project. It's done. I'm going to pick it up next week anyway, as everybody does, rewrite it. But I needed to close the case and put it on my portfolio because I think it's at least something cool. You know, I doubt a hiring manager would care, but who knows? That's it. Hip hip hooray.